We'll do a quick review of what we had gone over in the last lecture. So this part is quite familiar to you. I'm not going to drag you through all of that. All of you know that scaling improves performance. However, we wanted to see what happens when you scale interconnects. And there we found that the charge time, which is of the order of RC, remained unscaled. Not only that, when we looked at the histogram of various wires which exist, we found that this unscaled delay is in fact for local interconnects. For global interconnects, where the length does not scale down but goes up, the delay increases very, very sharply indeed, of the order of L squared. That is not takeable. That will limit the performance of our systems quite drastically. So this L square dependence was an area of particular concern, and then we looked at buffer insertion, which is a technique that we use in voltage mode. So that at regular intervals we will insert buffers, and then there was a trade-off. If we insert too many buffers, then we will insert too much delay from the buffers themselves. If we insert too few, then we will be subject to the L squared delay. So there is obviously an optimization, and we had worked out exactly what the optimization is. There were various concerns that we talked about. We talked about the signal integrity concern, in which there is crosstalk between signals, and we also talked about timing closure. Okay, so that kind of, and we had done some actual optimization, etc., etc. So we now begin with a new suggestion. We had looked at low swing voltage signaling, and we found that by limiting the swing, we can gain quite a bit, both in power and in delay. One nice thing which we didn't discuss last time was that this optimization of buffer insertion, it remains with the low swing signaling. What happens is that the wire delay, the RC time constant remains the same, but the delay refers to a voltage change which is much smaller now. Therefore, the delay becomes smaller by the factor V divided by delta V. Okay? So, same RC time constant, but now you are charging over a smaller voltage difference. So, as a result, it happens quicker. So, you scale down the wire delay, but you scale down the buffer delay by the same amount. So, as a result, the critical length after which you have to do buffer insertion, that remains the same. So, if you have a laid out circuit, you do have the option of dynamically reducing the voltage swing without going too far away from the optimization. Okay? So that is a nice thing, that you can lay out a circuit and so on, and you can have built-in circuits which will evaluate the power and the speed and various things, and now you can, depending on the noise condition, if you have some circuit which can detect how reliable your transmission is, then it can scale down the delta V to the appropriate amount without going too far away from the optimum point of buffer insertion. No, that will also go down, because the voltage change is smaller there also. This is the usual scaling. So dV by dt, which is C dV by dt is scaled down current, but because C is scaled down, dV by dt remains the same. So therefore, it is dV by dt which will remain constant, but the voltage change is smaller. Therefore, the buffer delay will become smaller. Okay, so both in fact scale by the same factor, because both of them, the d by dt of voltage is determined by RC constant in one case and by I by C in the other case. Okay, so those haven't changed when you change the voltage swing. Correct. So therefore, because the voltage swing is now much smaller, you will change both delays roughly in the same order. It is in the voltage, in current mode, you will strictly scale them in the same order. In voltage mode, what happens is that one is rather exponential, so you don't quite scale in the same order. But if delta V is small compared to V, it's quite linear. So therefore, then it becomes, the optimization becomes delta V independent. Okay. So now we suddenly wake up, rub our eyes and say, I got an idea. Why don't we do it differently? We did discuss it towards the last part of last lecture. that why don't I keep the voltage dead steady? If you are saying that reducing voltage swing improves everything, then why do I have a voltage swing at all? Let me keep everything dead steady. So then everybody rises up in protest. There are two problems. One, if voltage is not changing at all, how will you tell a 0 from a 1? Okay, so the answer is that don't look at the voltage, look at the current. The current can change. So then you throw up your arm saying Ohm's law does not permit you to change current without changing voltage. And you turn back and say, no, indeed it does, provided R is 0. Okay, so if we can somehow find a circuit whose input impedance is close to 0, then indeed we can do current mode signaling. That means we will let the voltage change as little as possible, hold the voltage constant, but change current because the input impedance is 0, and therefore the delta V corresponding to a delta I is 0. Okay, now we don't have the bother of charging up all these large capacitors which are along the wire and so on. Therefore, we'll reap the benefits of speed as well as power. So therefore, there is a fair amount of promise in this suggestion worth investigating. But if you look at the physics of it, actually the results are somewhat pessimistic, because it turns out that what capacitance does to voltage, inductance does to current. Okay, so actually it is the quantitative advantage that current mode has, because it turns out that the inductive effects are much smaller than capacitive effects in general. Part of it is this, that after all, when you come right down to the physics of it, the average dielectric constant is like that of the oxide, which is about 4. Okay, whereas the average mu is like 1. None of these materials is magnetic. So in short, the magnetic effects are much smaller than capacitive effects. You can, if you scaled everything, and it turns out that till fairly recent technologies, this is true. While inductive effects cannot be ruled out, inductive effects are not the dominant effect. Capacitive effects are. They limit the speed. However, as we go to futuristic technologies, this objection cannot be waved away so glibly. Right now we can, but eventually that will be something that we have to consider. In that case, the rate of change of current will become the limiting factor because of the inductive effects. But right now, we don't have very strong inductive effects. Can I now use current? So once I have suggested this, now I sit back and admire my own handiwork. And I say, look, now I can do even better. If I am signaling with current, the voltage is not changing at all. Then why do I have to have only 2 values of current to signal a 0 or a 1? I can have 4 discrete values of current. And on the same wire, depending on how much current I am pumping, I can signal 0, 1, 2 or 3. Okay, to take one example. That means the receiver now doesn't need an extra wire to receive 2 bits. It just has to have the capability of measuring current. Okay, so if and these are the DACs that we have done. Essentially we have an ADC DAC which is very fast, and 2-bit flash conversion is quite easy. That we have seen, not a big deal. So therefore, essentially we use, and this is what makes it mixed signal. So why do we use a digital circuit to convey information? Why don't we use an analog circuit? Then I'll have a 2-bit A to D to A conversion at the transmitter and a 2-bit A to D conversion at the receiver. Now I'll use a single wire, and because the input impedance is 0, the voltage will still remain 0, and depending on whether I receive 0, 1i, 2i or 3i current, I will now be able to receive 2 bits. There are party spoilers to all arguments. There are for this argument also. So there are people who turn around and say, well, if you can do that, you can do it for voltage as well. Why don't you do it with voltage? Then what's wrong with voltage? That means that, okay, 0 to 0.5 volts is 0, 0, 0.5 to 1 volt is 0, 1, 1 volt to 1.5 volts is 1, 0, and 1.5 to 2 or 1.5 to 1.8, whatever you have, is 1, 1. You could have done it in voltage mode, right? But we have a winning argument. What is the winning argument? That as the technology changes, voltages are scaled down further and further. Therefore, the headroom in voltage shrinks, as we go to higher and higher technologies. And therefore, each delta V will become even smaller and become comparable to noise. Okay? So then you say, okay, why doesn't that apply to current? And the answer is that whatever the voltage, you can still design circuits which will have large amounts of current. That is not being scaled down. Okay? So you have small amount of voltage, and if you can have appropriately sized transistors, then even in scale down technologies, in fact in scale down technologies it is easy because mu Cox is much higher. So therefore you can send larger amounts of current, and because you have a total amount of current which can be quite large, you can subdivide it into 4 fractions and happily have different levels which can be easily distinguished one from the other even in the presence of noise, and send multiple bits. Okay? So suddenly we have found an advantage which we did not have earlier in voltage mode. There will be many such advantages. So then what is it? So we are now sitting here and dreaming about it and drooling, saying current mode has now all these nice things. First, I am not charging up and down the line which was unnecessary overload on me, therefore I am not spending so much power. The second thing is that when I inject current at one end, and because the voltage is not changing, therefore no current goes to charge parasitic capacitance. So as soon as I inject current at one end, there is very little delay for seeing this current come out at the other end. Okay? It is not the same electrons which we insert at this end which come out at the other end, but as soon as I insert some electrons at one end, some electrons drop out at the other end because no current is being taken out, right? So overall this is expected to be low power, fast, and at the same time reduce the amount of area because I can use one wire for 2. Okay? So surely this is something that we should investigate. In fact, it was this idea that I had some time back, and the work that I am going to describe today is largely done by 2 students who are working with me, Supreet, who was an MTech student, and Mashnil, who is doing her PhD on this. So we will of course look at what the rest of the world has done, but this is our child, so we are particularly proud of it. So this is the idea that we started out with. Let me hasten to add that this idea is not ours. Current mode is quite old. It is only applied to this interconnect problem like this and specific solutions that we wanted. That is our work. But let me not be immodest and claim that the basic idea itself is ours. However, we have taken the technology quite a bit forward in this. Okay. So now, what is our sales pitch? That there is no voltage swing on the wire, so dynamic power is negligible. No charging and discharging of interconnect capacitance, therefore latency is lower. Multiple current levels, therefore higher throughput. In the same amount of time I am sending 2 bits. So I have not only reduced the amount of area, I have multiplied by the throughput by a factor of 2. In the same amount of time the current changes from 0 to 1i, 2i, 3i, whatever. But in one time, in one clock bit, I am actually sending 2 bits. So therefore my throughput is higher and I have lower interconnect area. So this is very good, very tasty. Let's try it. There is one little problem. You need an amplifier with 0 input impedance. Okay, so all of this will be a pipe dream if you did not have an amplifier which can provide 0 input impedance. In fact, we would like an amplifier which would have slightly negative impedance, which when put in series with the resistance of the wire will give me 0 impedance at the transmitter. Okay, so the total impedance seen by the transmitter will be 0. Okay, so naturally when we got this idea, I started looking in the literature where is a negative or 0 input impedance amplifier. So in this lecture I am actually telling you a story because it tells you how small the world is and how various people meet up in the arena of research. Apart from the dry teaching stuff, you will find a good story here. So this is what we are suggesting: 2 bits, A to D converter, D to A converter, 1 single wire, A to D here and 2 receive bits out. So looking for the 0 input impedance circuit, imagine my pleasure when I found it, and I found it that this is a paper published by a person I had worked with as a colleague in the US long ago, in 1985 actually. So we shared the same room, worked together, and then he had gone to Korea, I had come back to India, and when I was looking for a 0 input impedance circuit, whose paper should I find? But Professor Chunki came. So, and the idea is very simple actually. So therefore, I was really sold on the elegance of this circuit. By the way, just to spoil your pleasure a little bit, Mashnil has gone and demolished this circuit, saying this is not the best circuit, and we have now abandoned it. But at that time, we really enjoyed the fact that we have finally found a circuit with zero input impedance. It's a very useful circuit, and therefore, let's have a good look at it. Many of you who have done analog design would recognize it to be a beta multiplier circuit. Okay, did you do a beta multiplier in your analog circuit? You've derived? No? Okay, I will do it quickly because half the class would have done it. Have you? All right, doesn't matter whether you have done it and remember it, whether you've done and forgotten it, or you've not done it at all. We'll do a quick review of the beta multiplier. Okay, so let's do that first. Okay, it is not exactly this circuit. This is a modification of the beta multiplier. Let's look at the beta multiplier. There is more circuitry here, but I would like to pause here and essentially discuss what we are talking about. The idea is that we have actually two current mirrors. If you just look at the top, this is a current mirror, and if you just look at the bottom, that's a current mirror too. Okay. So essentially, the beta multiplier is the result of somebody asking himself, what happens if I feed a current mirror? Current mirror requires a reference current, right? One reference current goes in, the other is the output current. So what happens if I feed a current mirror by another current mirror? So that the reference of one becomes the output of the other, and reference of this becomes the output of the first one. Okay? So in some sense, it is what is in the voltage mode of flip-flop is this circuit, right? In voltage mode what happens? 0 feeds a 1, 1 makes it 0 again, right? So the two are live happily with each other. Essentially it is the same thing. There is this current mirror. Let's say that these two are matched. Okay, in reality when we make the beta multiplier it will not be matched, and forget this resistor right now. Okay, so then it is truly a current mirror feeding a current mirror, right? Now if let's say that the current through this is I, then the current I flows here, and that induces the current I here, and because this is I and this is a current mirror, this is also I, therefore this right hand side is also happy. Okay, so that means that this system is stable, right? But wait a minute, there is a problem. That means this system is stable at any current. Yeah, why not? No, right now we are talking, say R is not there. Okay, so if there is no R, then because there is a current mirror feeding the current mirror, once you start it up at some current mirror, it's a self-sustaining circuit, right? So it can stay at any old current, it is happy keeping the current. It's a current keeper circuit, just like a flip-flop is a voltage keeper circuit. You give it 0, remains at 0, give it 1, remains at 1. Here you start it off at some current and it remains at that. That is where we have a bit of a problem, because what is the likely value of current that this circuit is going to start at? 0. So it is happy. If both currents are 0, no current is flowing, everything is off, this circuit is not working at all, but this guy is happy. Okay, so you can't afford to make him that happy. So what we do is that this circuit always requires a startup circuit. Okay, we will worry about the startup circuit later. So you inject some current into it, right? Then this will be happy. However, you don't want it to be happy at any old value of current. Okay, so it is this arrangement which then determines what will be the current. You put a resistor here. Okay, so let us just do a quick derivation of this. Let's say these two are matched. Okay, these two currents, meaning the P channel is 1:1. Therefore, the currents in the two arms are the same. Now, which transistor should we make larger? These two are a mismatch because one has a resistor, the other does not. Okay, Which transistor should we make larger? Make up your mind. The one with the resistor should be larger, because it should pass the same amount of current with less voltage, because some voltage was eaten up by the resistor, right? So the larger transistor should be the one. So let's say that it's larger by a factor k. Okay, the geometry ratio, and this is what makes the circuit so much better. That is to say, the geometry ratio is 1:k. It is a ratio metric circuit, doesn't depend on the absolute value. Okay, so now what is the overriding equation for this? That VGS1 that is equal to VGS2 plus R times I. Okay. So this now has a unique I solution because of the introduction of this factor. This will now not be satisfied at any value of I. This will require a particular value of I at which this is satisfied. In short, you can write VGS1 as root 2I by K1. Okay, let's say that the ratio of geometry is M and not K, because there is this K of the transistor. Okay, so this is root 2I by K1 plus VTN, of course. This is the drop across it. I don't have to do all this with you. No, this is Vinith's contempt for you. The VGS of a transistor, a saturated transistor, is root VTN plus root 2I by K, right? So this is equal to same current, but K1 times M, right? This is M times larger. This transistor is M times larger plus R times I. Plus VT. Yeah. VT will in fact cancel. So VTN will cancel from both sides. Right? So now I can multiply perhaps by root K1 by T, and let us call root I to be X. Okay? So then what do I get? I am multiplying by K1 by root K1 by 2. So I will have only X left over here, only root I left over here, right? So X is equal to, what am I, then again root I is X here, right? And root K1 by 2 has been multiplied, right? So this is X by root M. Right? Plus R into root K1 by 2, right? I am multiplying by K1 by root K1 by 2 throughout. So R times root K1 by 2 and I, which is X square, right? Because I am putting root I equal to X. This gives me a quadratic in I, which I can solve. Okay? So I will not drag you through the solution of this, but that means there is a specific value of current at which this will now be satisfied. And what will that depend on? That will depend on these coefficients. Okay? It turns out that it depends only on M and not the actual value of K. Okay? So it depends on M and on R. Because M is a ratio, therefore it can be set very, very accurately. Because if one transistor is changed a little bit, the other transistor, it's a ratio of geometries, right? Mobility cancels out, because it is, what is M? K1 by K2, which is mu Cox W by W1 by L1, the other one is mu Cox W2 by L2, right? So mu Cox just cancels out. So essentially what it means is that the process parameters cancel out in M, and as a result this is very robust with respect to process variation. Okay, the geometry can be set quite accurately, so M can be set quite accurately. So this is the ordinary beta multiplier. Okay, now you can see that it actually has positive feedback. That is how it sustains like a flip-flop, right, in voltage mode. And therefore if this R is made too small, then it might become unstable. indeed that is where the germ of the idea comes, that this will actually give us an input impedance which is very small, okay, because of that feedback. Alright, so this is the standard, so this is not part of this course, this is part of your analog course, right. So this beta multiplier circuit is very well known. What we now do is get rid of this on purpose, make it unstable, but now we don't feed it from the power supply, okay. Remember, what are we trying to do? We are trying to detect a current in the wire, right, the amount of current in the wire, and we are trying to bias this wire at some VDD by 2. That is what we said, right? We will hold this wire at some VDD by 2. That means simultaneously we are trying to read the current in the wire and we are driving it with a voltage, right? We are trying to keep it at a voltage, and at the same time, in keeping it at this voltage, how much current is flowing, that is what we need to measure, right? That is the circuit that we really want, okay. So you got that, the scenario. So for that we use this beta multiplier. Then the analysis is quite simple actually. Let's do the small signal analysis. Remember, now we are not doing a DC analysis. By the way, just as a side effect, you would notice that the beta multiplier actually gives a current which is, meaning gives you a constant GM circuit. That means if the current given by it, if you feed it to another similar transistor, then it turns out that in spite of process variations or whatever, its GM will be the same. So therefore the beta multiplier is also called the constant GM circuit. So let's analyze it in terms of its GM in small signal. So now what have I done? I have opened out, this top was earlier going to, the resistor has vanished, and this top was earlier going to VDD, but now I connect this to the wire. This is the receiver, so I will connect this to the wire, okay, interconnect, and give a reference voltage here, okay, and the ratio of both the top and the bottom is 1, okay. Later we will see how we make it 1. Right now maybe we will see that the ratio could be k, but later we will bring it to 1. So there is one thing that you see, notice that there is a VTN plus root 2I by k drop here, right, source to gate, and VTP plus root 2I by k here, right, and VTP plus 2 root I by k here if the two currents are the same. As a result, this voltage is constrained to be the same as this voltage, right. What is really happening is that this transistor is acting as a source follower, PMOS source follower, right, this is the source. So it is acting as a PMOS source follower and therefore driving the output with very low output impedance. Therefore it will force the voltage at this point to be fixed at whatever Vref is, right, because Vref minus Vtn minus root 2I by k will come here and the same drop will be here. So this will be a low impedance output driver, source follower like thing, which will force the output at that voltage, okay. So this is the DC analysis. So whatever Vref you have here, this voltage will be maintained at that. So therefore now we got that condition which we wanted, that the interconnect is maintained at a constant voltage. Now let's see what happens to the current. So we are forcing a current. Suppose there is some current source driver from the other guy. So the voltage is held constant, but some current is being sent, small signal current, change. So let us do the small signal analysis of this. So let us say that these two currents are not quite the same, I1 and I2 in general case. So what is I1? I1 is a fluctuating current, by the way, small case I, right, it is a small signal I, not the actual milliamps flowing through this, but the deltas. So what is I1? This is equal to I1, if this is V1, these are also, small v is also the fluctuation, delta V, right. So Gm times delta V should be I1, right, all transistors are saturated, so Gm times delta V, that should be I1. So this is the current going through this. Also, GMP, if the fluctuation here is V, right? So we are not assuming the fluctuation there to be 0. We are saying that the fluctuation on the line because of this varying current is V. Okay? And the fluctuation here is V2. Right? So what is I2? I2 is GMN2 times V2. Correct? That is I2. And it is also equal to, if you look at this, is minus GMP2 times V2. Right? Because the V2 now will have a negative sign for the p-channel transistor. That same fluctuation. So while the current of one will increase due to variation in V2, while the current of one will increase, the current of the other transistor will decrease at the same time. Right? So therefore the current fluctuation through this, which is I2, right, that will be GMN2 V2, because V2 is the fluctuation here, right, and this is the GM of this transistor, and that is equal to GMP2 times V2. Okay? So then I can just substitute in I1, right? So this, what we did not know was this V2, right? That is the unknown. We know V, but we did not know V2. So we substitute for V2 from here. Okay? So what is V2? That is I2 divided by GMP2. Okay? Or I1, right? So V2 is then minus GMN2 by GMP1 into V1. Okay? GMN2 V1 upon GMP2, right, into V1, that is equal to V2 from this equation. Correct? But what is V1? V1 is I1 by GMN1 from here, right? So I put that, and finally what I get is that V2 is minus I1 into GMN2 divided by GMP2 into GMN1. Okay? Just comes from the balance of these. These two are series connected, and these are current mirrors. Comes from that. We are assuming that all transistors are saturated and there are no early voltage effects and so on. So then I put this value of V2 here. What are we up to? Why are we doing all this algebra? We are trying to relate V and I1, because that will allow us to calculate the input impedance, right? The input impedance is the ratio of V and I1. So this equation will allow us to do that, except that we didn't know this, right? This equation will allow us to relate V to I1, and that is the input impedance here, because V is the voltage fluctuation and I1 is the current going there. So the ratio of this is the input impedance, which is what we want. The thing which was missing was that we didn't have V2, right? So using this second equation, we have now evaluated V2 in terms of I1, which is fine, right? So we just substitute it there, and what do you get? I1 equal to GMP1 V1, GMP1 V, right? And this minus and minus will cancel, so you will get plus GMN2 by GMP2, GMN1, and this GMP1 will come, and times I1. Okay? So now you define this ratio to be some gamma. Okay? So we define this ratio to be gamma. Then what do we get? I1 into 1 minus gamma. We take it to this side. Right? So I1 into 1 minus gamma is GMP1V, and finally therefore our input, which is V divided by I1, is 1 minus gamma divided by GMP. If I can make gamma equal to 1, then I've got 0. Okay? So essentially what we have done is that in this case the current was due to these two voltages together, right? So just substitute that and put it, finally you get this 1 minus gamma by GMP1. Okay? Now if gamma is equal to 1, then I'll get 0 input impedance. If gamma is slightly greater than 1, then I can even get negative input. Okay? In general, I don't want negative input. Why don't we want negative input? What's the problem? Right. So the point is therefore that we would like to be close to 0 but never become negative input impedance. Right? What is this positive feedback? What do we physically, this is all textbook stuff, man. Negative input impedance. What does negative input impedance mean? Yeah. So as I change the voltage, as the voltage decreases, the current actually increases. Right? And because of that feedback, the voltage feedback that I have. So essentially what it means is that when the input impedance becomes 0, then to create a certain amount of current, I don't need a voltage change at all. Okay? You just dhamkaw it a little, don't actually move. And in response, the current starts increasing. Right? Because of the positive feedback. So actual delta V is 0, but because input impedance is 0, the current can now change. Okay? In reality, you don't quite want it to be that, because you want this signal for changing current coming from the signal and not from noise. And this circuit has no way of distinguishing signal from noise. It might start changing current suddenly by large amounts in response to noise as well. Right? So therefore, you don't quite take it to negative value. That means we must keep the gamma slightly less than 1. Therefore, the whole business is how controllable is gamma. Because if gamma can be set very accurately, then I can dare to come very close to 1. But if gamma has lot of uncertainty, then I have to keep some safety margin and remain away from 1. Right? So that is what we want to see, how robust is gamma. But what is gamma? Okay? So I don't have to tell you that GM is root 2 mu C ox W root 2 Ki. Right? So therefore what is gamma? It is the ratio of two ratios, GMN2 by GMN1, GMP2 by GMP1, and the ratio of these two. So what happens is that when you take the ratio of these two, notice that they both are N channel. Therefore mu N and C ox of the N channel transistor cancels out. What does not cancel out is the current. Right? Because we don't know how much current is flowing. So essentially GMN2 by GMN1 is the ratio of the two N channel transistors, because both are N channel. Therefore mu and C ox cancels for both of them. However, the currents are potentially different in the two. Right? So therefore this ratio is root I2 by I1. But similarly GMP2 by GMP1 is also root I2 by I1, apart from geometrical factors. Right? So when you take the ratio of ratio, because the N channel and P channel are in series and the current therefore is the same, so now the current cancels out. You got it? When you took ratio of N's, then the technological parameter cancelled out, and when you took the ratio of ratios, then the operating point cancelled out. Okay? So as a result, this gamma is very, very robust. It is dependent only on geometry. Okay? So it's also in that geometry, it is a ratio of ratios. Okay? In fact, it's a ratio of ratios. This is W by L, it's a ratio. W by L of N2 divided by W by L of N1 is a ratio of ratios, and then ratio of such two quantities in P, N and P, right? So it is essentially a triple ratio. Therefore, things are quite nicely ratiometric. If everything changes by the same amount for all N channel transistors, for all P channel transistors and so on, this will be least bothered. Okay? And it is totally independent of mobility, therefore it is independent of temperature. It is totally independent of C ox, therefore it is independent of device to device variation and so on. It depends only on the geometry. That's very good news. Because now, just by controlling the geometry, I can bring gamma as close to 1 as I dare, depending on how controlled my geometry is. And indeed, if I find that it was a little, once or twice I may have to adjust with the technology, but I can get a value of gamma, and then I am sure to reproduce this value from one run to the other, because it depends on nothing but geometry. Therefore, this is a very good circuit. Okay, so it is now possible to have zero input impedance circuit. Now you can go ahead and make current mode circuits, which will determine the amount of current. So what have I got? This current, C is a zero input impedance. Okay? As a result, when this current fluctuates from 0, 1, 2, 3 delta I, the voltage here doesn't fluctuate at all. In fact, it stays put at the value of Vref. Okay? And that is what the beta multiplier does. But then how do I measure the current? That is all very well that you have loaded it with zero input impedance, voltage doesn't change. But I do want some output indication of how much current had come in. And that I can simply do by mirroring this current. So this I out will come. Notice that this ratio need not be 1:1. So I can have a huge ratio here. So I can amplify that small delta I locally in one small transistor and now sense this current by putting a load there and get a voltage up. Right? So this is what we end up doing. In short, this is the weak point of this. That means I have to convert this current to voltage. Okay? And the current comparison, I have to compare this current to delta I, to 2 delta I, to 3 delta I and give an output whether the output is 0, 1, 2 or 3. Right? This comparison tends to be slow, unfortunately. Okay? Current comparators unfortunately have a moment of indecision if the two currents are equal, exactly equal. So that makes this circuit a little slow, which enabled Marshall to throw out this wonderful idea. However, this circuit works quite well, and if you can afford to have a delta I which is rather large, then this is a very effective circuit. Okay? So what I am suggesting is that you have 3 mirrors from the previous circuit and you have a reference IRF1, IRF2, IRF3, and since it is a current mirror opposing a current mirror, whichever current is high, it will just swing, it will charge some voltage to either VDD or to ground. So now you will get a voltage mode signal, and now you can put a decoder which will say whether it is. So this is essentially your thermometer to binary decoder, right? Because the output will be either one comparator is 1 or 2 comparators are 1 or third comparator is 1. So you put in a thermometer decoder here, right? And that will allow us, and it's a small circuit, therefore you can make very fast circuits. We have now looked at the receiver. So there are two kinds of receiver possible. One receiver I told you, but there is actually, after all, what we are doing is A to D. So why not use an A to D kind of thing? So this is essentially a pipeline converter. So it is just make a pipeline converter for 2 bits. So essentially the first one, and then depending on that first one, either you subtract I0 or don't subtract I0. Okay? So you can make any architecture. This is one architecture. For 2 bits, what's the big deal? You can make a 2-bit pipeline converter like nobody's business. Okay, and it will be quite fast. So that is what you can end up doing. The disadvantage of this is that it takes a little more current. The advantage is that nothing changes. The current is only steered. Okay, the total current always remains the same. It's fed by a current, so the total current always remains the same. The current is steered either through this path or that path. Okay, so it's a very fast circuit. Similarly, for transmission, what can we do? I can have an I0 source and a 2 I0 source. Okay, so I have these 2 sources and I steer this current either into the interconnect, which is a virtual ground, zero input impedance, right? So I either steer it into the interconnect or steer it into a node which has an equivalent voltage. Okay, so I size this transistor so that the holding voltage here is the same as the interconnect voltage, which is Vref, right? So size this transistor to be very close to Vref. Then the current flowing is always the same and the drain voltage is always the same, whether it goes this way or that way. Therefore the source voltage will always be the same. So as a result, right, depending on these 2 transistors are identical. So either this transistor is on or this transistor is on, right? So what will happen is, and the drain voltages are also the same. So for the same, because I have biased this so that this comes to Vref, right? Choose the size such that it comes to Vref. So that means the drain is Vref here, drain is Vref here. So irrespective of which transistor is on, you see the same conditions always. Therefore the source voltage never has to change. Therefore even internally the voltage is dead steady. Even as you switch, the voltage is dead steady. this source voltage doesn't ever have to change. So as a result, I have a very fast circuit where voltages never have to change and current switching is very fast. Okay, so as a result, I have a very fast transmitter. But of course, that means this will draw 3I0 all the time. It's a current source and that much current is being drawn all the time. So therefore, it will draw 3I0 all the time. On the other hand, if I am a little sensitive about spending so much current, I can have a switching transmitter in which I have a series. So this is the bias transistor and I have a switch which is either on or off. So if both are off, both current sources will be off. If one is on, this is the less significant, then I0 will flow, otherwise 2I0 will flow, and if both are on, 2I0, 3I0 will flow. Okay, but in this case the amount of current is changing, therefore voltages will change internally in this circuit. So I have both choices. In short, I have two options. In this case the average current is 3/2, in the previous case the current is always 3I, right? So the current doesn't change. In this case the average current will pulse depending on what the data is. Okay, it can be 0, 1, 2 or 3 and the average of that will give me some 3/2 current drawn by. Okay, I think let's stop this here at this point. These notes will be available to you. I'll put it up on your Moodle site. Okay, so this covers essentially what we did last time and this time. So the point is that, however, we have found ourselves blocked at one point, and that is current comparison is slow. So what has happened is that now I have this situation. Let's say that I have I, 2I, 3I and 0. That means I must put this reference comparison current to 0.5I, 1.5I and 2.5I, right? That means suppose I have I flowing here and 0.5I here. Okay, so let's talk of one bit initially, not multi-bit. So this I could be 0 or I, right? So either 0 or I. Okay, and I have a capacitive input here. Okay, capacitive load. So this 0.5I is my reference current, locally generated, and this is the line current mirrored from that beta multiplier, which could be either 0 or I. So this being the case, when this is 0, what will happen? This current will charge up this capacitor towards VDD till this current source switches off. Okay. On the other hand, if it is I, what happens? A net current of 0.5 discharges this capacitor. So the output will be rail to rail till the transistor switches off, right? So that is very nice. However, what happens if because of noise or whatever, if these two currents are equal, because of mismatch, noise, etc. Should these currents become equal, then they will take infinite time to resolve, right? In short, the mismatch between the two currents, which is of the order of delta I by 2, that determines the speed of this circuit, right? That means delta I determines the speed of this circuit. So if delta I is large, then my power consumption is large, but on the other hand my speed is good. Okay, so I can now make compromises. Is speed important or power consumption important? And accordingly we can now make this very fast or make it very low power. Okay, in that case the switch. And notice that the rest of the interconnect design doesn't change at all. Even the beta multiplier does not change. Okay, what changes is the current multiplication ratio in the current multiplier. Okay, recall what we had was that this is that beta multiplier final n channel transistor. These are the two n channel transistors. This is the beta multiplier. Okay, the corresponding p channel transistors on top. So what I do is I take this voltage out and now put a transistor here. So this is my current source, this one, and I put a IREF here. So this is the beta multiplier. I have my Vref here, I have the line here, and this current is just being mirrored in this. Okay. Now by adjusting this ratio and choosing the appropriate value of Iref there, I can, so notice that the line current has not changed. Line current remains the same, but the comparison that I am doing is on a scaled up amount of current. Therefore, I can make a compromise between speed and power to any extent. To give you an example, suppose 15 microamps of 0 was coming here. Suppose I have a 10 to 1 ratio. That means I have 150 microamps of 0. Then I can have a 75 microamp source here. Right? So when this is 0, I have 75 microamps charging the output capacitance, and when I have 1, that is 150 microamps, the output, there is a 75 microamps discharging. Okay? Suppose I make this ratio 20, I will have double the amount of current. Okay? And the rest of the design before this point will not change at all. All that will change is this ratio, this current multiplier ratio. Okay? So I can choose anything that I want and choose, make a compromise between speed and power. Got this? So on the other hand, however, it means that you can't have both. You are limited to this. In some sense, if you look at it, this is very similar to low swing voltage signaling, right? Because my voltage swing on the line is not exactly 0, because I cannot dare to bring the input impedance exactly to 0, right? So in that case, there will be some residual resistance, at least the ohmic resistance of the wire and so on. So there will be some delta V. All that has happened is that now I can afford to have a delta V, which is much smaller. Because my input impedance is very small, arbitrary noise will not be able to induce voltages in this. This is kind of a grounded line, right, connected with practically 0 input impedance to ground. So as a result, there is not much fluctuation due to noise. So therefore, I am fairly robust with respect to noise, and therefore I can afford to have a delta V, which is much smaller. That is one difference from the voltage. The other big difference is that the impedance that you see in case of current mode is low, in case of voltage mode is high. Otherwise, both of them limit the voltage swing on the line. Okay. However, in this case, we have the luxury of restricting the voltage to a much lower voltage. This is not susceptible to noise. What happens is that if you have something connected to ground through practically 0 input impedance, so what happens is that the noise sources are like high impedance sources, stray capacitance and so on. So essentially what happens is that suppose this is your stray capacitance. Okay, what happens in the voltage mode? This is your aggressor voltage. Right, in voltage mode this goes to a transistor. This is your CGS. Correct? So the voltage division takes place here and you get relatively large voltages. Right? In the current case, what happens? You have the same V aggressor, okay, same capacitance, same wire, except that it is coming down to an input impedance which is very, very small. So as a result, the noise voltage which results at this terminal is very small. Okay, that is one thing. But in fact, things are even better. What happens is that the switching wires, the aggressor itself is not switching by a large voltage. The nearby wire, the voltage is not switching by a large voltage. Right? So it is essentially being kept within some small delta V. So even this V aggressor is now much smaller. So as a result, the overall noise in your system is way below what it would be in the voltage mode, even with reduced swing. Okay, so that is the great advantage here. Each line is nice as far as voltage is concerned, it's just sleeping at a fixed voltage and is neither receiving noise nor giving out noise. Okay, so following its punch shield. No aggressor, no real aggressors, no real victims. That is the great thing about this. Okay, so therefore overall noise is low and therefore you can afford to have delta V's which are much smaller. Okay, hence either use I's which are much smaller or both I small, R small. Okay, so you do that, now you are fairly noisy in here. It will not cause a flicker, but it is true that the delay will be dependent on the mismatch. That doesn't cause problem, because what happens is that after that there is a voltage mode buffer. So what the digital circuit sees is the output of the voltage buffer, and this voltage buffer will not consume too much power because its input eventually goes fully to ground or to VDD. It is just that the time is a little different. Okay, so if it is a digital circuit, then as long as the output settles by the time the clock comes, you are fine. Okay, however, it is true that the delay will have that jitter, but this jitter will become infinite should the two currents become exactly equal. That means if this current and this current are exactly equal, then the output will stay put at VDD by 2, will neither be charged nor discharged. So will take infinite amount of time to go to 0 or to 1. That means it can become very, very slow if the two currents come too close to each other. Okay, and this may happen because of mismatches and so on. So essentially what it means is that this circuit has all the good qualities, low power, high speed, low noise, everything, but it is not very kind to mismatches. Okay, so it's due to mismatch. After all, this IREF is being generated locally, and this is coming from a remote situation. So therefore these two cannot be ideally matched. So therefore if they come very close to each other, then your circuit will become extremely slow. So your speed variation is very high in these circuits. Okay, so this is what enabled Marshall to throw out this circuit. Otherwise we are quite fond of this circuit, very nice, but that is the problem with this. Okay, so what can we do now? So essentially, by the way, just this is not very important, Marshall has taken a very simple circuit. She simply says that we will use this as termination. Okay, so this is essentially a diode whose impedance is given by GM, 1 by GM, okay, because the drain gate is shorted, and you use a large enough transistor, then you can make the thing low enough so our delta V's are not going to be 0. But the point is that we need both sides. Therefore what we have essentially is a circuit like this, where you have one N channel and one P channel terminator, N channel to ground and P channel to VDD. Okay, so you rub your eyes and look at it again. What circuit is this? This is just a shorted inverter. Right, because this is the circuit. So this is just a shorted inverter. Therefore where will it settle? To the trip point close to VDD by 2, but whatever is the trip point of the inverter. Okay, and that's good, because now for amplifier we can use another matched inverter, and it ensures that the bias here, the VDD, the resting voltage of this is close to the trip point of the second inverter, right? So what you do is you have one shorted inverter as the load, and then you give it to one inverter which is the amplifier and another inverter which is the final digital buffer. So this is in digital mode. Even though this looks like an inverter, it is actually an amplifier, and it helps to bring the voltage swing to a healthy enough level so that the P and the N in this is completely turned off, and this is the load. Okay, so it appears in layout as if there are three inverters to the incoming line. The first one is a shorted inverter where the input output are shorted, and you can see from the feedback as the input rises the output falls, therefore it draws huge current from the output, therefore its input impedance is very low, which is what we want. Input is given here. Okay, so this ensures that this output doesn't swing ever by a large amount, and it also ensures that this voltage is matched to the trip point of this. Okay. So as a result, you are sure, remember we had discussed this about robustness, that if instead of here you are somewhere here, then you will require much larger delta V. Otherwise you will be swinging there by the right amount, but it will not be distinguished. But here it is inherently matched to this, and therefore that means you are guaranteed to be somewhere here to be amplified properly. Okay. Of course that requires that the local matching at least should be good. These two should be well matched. Okay, and that is much easier than matching a transmitter which is at Timbuktu from the receiver here with millimeters of wire running between them. That is difficult, whereas here these two are physically adjacent to each other, and matching them is much simpler. Okay, so this is what we are now using in the current mode circuits that we use. Okay, in this business, however, you are never happy. You always want to gild the lily. So we said, okay, this is all very well, papers have been published, fine, what else can we do? So what we said was, what's your problem? Why are you worried about this interconnect? What is this interconnect doing to you? So what's your complaint from the interconnect? Why are you doing things to it? Delay. So that delay is coming from what? RC circuits. What is an RC circuit viewed as a filter? It's a low pass filter. So that's why I can't have high speed, because high frequency components are being reduced by this multiple RCs that I see, right? So therefore the line is like a low pass filter, therefore it is not very fast. So the point is, can I not put a compensating filter at the other end which is actually high pass, so that overall this becomes band pass? Can I not pull the pass band frequency of this? So what do I need at the other end? I need a high pass circuit. Okay, and then what would a high pass circuit be what will it look like for a high pass circuit? Capacitor in series, but that won't do, because eventually that, you put a capacitor in series, you will get only a pulse. Okay, you won't get a level. So what you can do is put an inductor in series with the load, with the terminator. Okay, so if you put an inductor through which the current is flowing, so I have a current mode signal, right? And if I put an inductor here, what is the voltage across it? Omega L, right? If I is proportional to whatever, right? So for the same amount of current, the output will be proportional to omega. The higher the frequency, higher its impedance, same current flowing through it, the voltage will be higher at higher frequencies, right? This is I times omega L, right? Voltage equal to I times its impedance, which is omega L. So for a given current, it's a high pass by itself. So what I need is an inductor. Okay, so but where am I going to get an inductor in an integrated circuit? That is difficult. Where do I get an inductor? Fortunately, it turns out that if you look at our beautiful beta multiplier, it's actually an inductor. If you put a capacitor at the input, because of the positive feedback and the two GMs, it actually transforms that capacitance into an inductor. Okay. So you've heard of gyrator circuits in analog, it's actually a gyrator circuit. In fact, we go back and say, oh, that is why our beta multiplier was working so well. It had no business being so good. At that time we were just too busy celebrating. But the reason why it is so good is, in fact, apart from doing everything else that we had talked about, it had also transformed the capacitive input impedance into an inductive inductance in a load, and that was a natural high pass, and that was compensating, and therefore it was even better than what we had thought. Okay, so the idea is that putting an inductor is not a practical proposition. You can't make inductors a very big, inconvenient to make, etc. You have 32-bit bus, each one terminating an inductor. You will have a chip the size of a small house in Bombay. That we cannot do. So what we can do is, of course, construct this inductance from active circuits, and a beta multiplier already does that. Okay, so that is very good. inductive termination is one solution. But you can go only this far with inductive termination. Okay? And the reason for that is the following. If the line has already dwindled down your circuit, your input at high frequency to a very low value, a high pass will equalize, but your signal to noise ratio will become very poor. You got that? What you are saying is that you have a low pass, the high frequency components have already been brought down by that low pass. Now you are saying that you will also kill the low frequency and overall make the signal very small and then amplify it. That's in effect what you are doing in this equalization, right? This high pass is actually, it cuts the low frequencies, right? So then your signal to noise is bound to suffer. So then we scratched our heads and said, what can we do? And eventually we kicked ourselves and said, why didn't we think of it before? Why do we equalize at the receiver? Why don't we equalize at the transmitter? Send much more high frequency than necessary. Now your signal to noise won't be too bad, because this low pass will kill your high frequency components. After killing, you will have equalized performance, right? So in short, if you know the transfer function of your line, then suppose you have a transmitter whose transfer function is the opposite, then between the transmitter and the line you will pass high frequencies properly and you will receive at full amplitude the signal. Okay, so what do I need? If the output is like this, assume that we treat it like a single RC. Okay, this is frequency, this is response, right? So if the line is like this, I need, okay, in fact it is not like this, it is just continues to come down, right? First pass, first pole, one pole, single pole system. So really what I need is a system transmitter whose transfer function is like this. Okay, so that when I take the product of the two, I will get constant with frequency. Okay, so but this has a basic problem. I need essentially an active circuit whose gain remains high at very high frequencies. Okay, and becomes higher and higher as the frequencies become higher and higher. I want higher and higher gain as the frequencies become higher and higher. That's not easy, because after all frequency response of my circuits is limited. Okay, so what I can do is I have to make a compromise. That is to say, I'll have something whose pass band is somewhat like this. I can't have very high gain at beyond some cutoff frequency. This is essentially, I have already reached the FT of my transistors. But till that time, let me boost the gain. So this is all very well in analog, but we don't like to have analog circuits and filters and so on. That, you know, those are not appropriate for the frequencies that we are talking about. So in time domain, what do I mean? Something whose response is like this, what will it do in time domain? Suppose you have something which accentuates high frequencies, right? So what will it do? Instead of a square wave pulse, square pulse for 0 to 1, essentially it will do this, right? That is what you are asking for, right? And that is where the solution is. In this case, this trick is not our actually we had also come at it, but we got beaten on this trick. This is called dynamic overdrive. Okay, we got beaten in the sense that we got beaten like nobody's business. We had no business not knowing it. All of you have done 8051. All of you have done 8051 ports. Okay, yes, no, maybe you've done. So what is the famous thing about 8051 ports? The port driver. You have two drivers. Whenever there is a 0 to 1 change, there is one high current driver which dumps a huge amount of current for a short time. And then, so that means, when do you need current? When the voltage is changing. To retain the voltage, you require very little current, right? So as a result, what you need is essentially, if this is a pulse, during this time, you need to dump a huge amount of current, and during this time you have to withdraw a huge amount of current. Okay, so essentially you have a transient driver and a steady state driver, both driving the same line. Okay, this transient driver is very power heavy, huge amount of current, but it is turned on for a very short amount of time. Okay, the other guy is a very easygoing low power thing, and its job is to maintain a 0 at 0 and a 1 at 1. Okay, in short, this is the low frequency amplifier, this is the high frequency amplifier, right? So in short, the digital equivalent of that is that when I want a square wave, I'll actually drive it like this. Okay, I will turn on my high current driver for a very short amount of time and the other guy for the full amount of time. Therefore, for this much time I'll get the sum of two currents, and at the other I will get only the average current, right? So if now this current is low and this is quite high, then I will not spend too much power, right? Because even though this is a high power drive, it turns on only for a short time, so the total energy consumed per cycle is quite small. Okay, so then, but on the other hand, this now has done what I wanted. That is to say, if you look at the frequency response of this compared to the square wave, then I have a much higher high frequency component because it looks like this. Okay, and indeed we simulated it. By the way, we got beaten in this application also. First of all, the basic principle we should have known, having done 8051 in all our early education, not in my case, I am pre 8051, but Marshall should have recognized it. But then we arrived at it in a very theoretical way, that oh, why compensate it at the receiver, why not compensate it at the transmitter, and when we did all the algebra, and then we kicked ourselves saying this is what 8051 does all the time. But what is worse is that by that time somebody had published a driver which uses exactly this. So it essentially uses current overdrive for a short amount of time. And this is what I mean by the Hindi movie component of this lecture. Who should it be but my own student, guy called Katoch. He had done a project with me some 5-6 years ago. He is now working at Philips, and he should be working in the same area. And before Marshall and I could go and design the circuit and publish it, we found a paper published by Katoch which did exactly this. Anyway, good value. He is also my student. So, but this is actually a very good idea, very easy to implement. And 8051 uses this idea. What happens is that there are ports and they have two drivers, and one of them has an XOR. So if the output is resting at a value different from what you are driving it to, then it turns on the high current driver. Okay, otherwise only the low current driver is turned on. So that is a much slower thing, but it does provide that. So this is something, because it is somewhat smart. So all guys who, it's a very favorite exam question for 8051 about describe port driver for 8051 and how it achieves high speed, etc., etc. And having done that all, we hadn't connected up 2 and 2 together and arrived at it. It took us too much time. Before that, somebody had published this idea. But anyway, this is one thing. So having arrived at this, then we said, look, we are always hungry. What happens if we combine the two ideas? That means we will have an overdrive transmitter and we'll have an inductive receiver. Okay? Isn't that even better? And the answer was a resounding no. It turns out that when you have equalized, you have equalized. So if you have a properly designed transmitter, then an inductive drive doesn't do too much. And when you have a properly designed receiver and signal to noise is already good, then an overdrive doesn't do too much. Remember, you only want to equalize. If the high frequency is more than that, doesn't help you too much at the frequency. The other part is that actually when you are sending data, somebody is generating this, right? There is no point in making an interconnect which is capable of operating at a speed which is much higher than your logic. Okay, so a little bit is okay, don't be too greedy and use up a lot of power and prove that I have got an interconnect which works at 4 gigahertz. However, unfortunately, I can't go above 2 gigahertz for my clock. Then what's the point of having a very fast interconnect, right? So it has to keep track with your circuits, and this design either with this or with that is quite good enough for that. It turns out that if you are looking for low power, low speed, then correcting at the receiver is better because it saves power. You don't require these high current dumps. If you are looking for high speed circuitry, then rather than doing it inductive input and then big amplification, that is not better. It is better to have an overdrive transmitter. So there is a difference and there are clear areas of optimization. So essentially for high speed drives where you don't mind spending a little more power, it is better to have an overdrive circuit at the transmitter end. When power is everything and still you want to have as high a speed as possible, then it is better to have inductive termination, and that means our beta multiplier is still not dead. You still want to use it. And if it is slow, then of course it doesn't matter because then the current comparator is not such a big limitation. So that is the overall resolution, which is where we are right now. So by the way, we have actually fabbed these circuits and one set of measurements have already been made, and we then slightly improved those circuits, and the second circuit is right now waiting at the customs, and Marshall is impatiently waiting for it to arrive so that she can measure it. But essentially these ideas have not only been shown in simulation but have actually been shown on silicon already. So these things work, and eventually the biggest thing that we now have to overcome is designer inertia. So the world, we thought the world would be jumping up and down because what did we start with? That this is the fundamental problem. So here we are saying, celebrating that we have solved your fundamental problem and we can now send data at low power and high speed and so on. And the world appears not so enthusiastic. We are the only ones clapping. And the reason for that is that the digital world is deeply suspicious of analog guys. This is the main problem of mixed signal design. So they would do anything as long as all circuits are digital. But then they say, oh, you are using analog circuits, so I am very nice, please take it away. So none of them is really, we described it to Intel and they said, yeah, how nice. And our papers have been accepted all over the place. But to this day, we don't know of any manufacturer who is actually using this for actual data transmission and so on. However, we hope that in a couple of years' time we will have enough data, and the main idea is the following. It turns out that the design is independent of the length of the wire. Okay, so as a result, you can say yes, it is analog, but that is no skin off your nose. I will do the analog design. I'll give you a library circuit. Now, like a good digital designer, you say I don't understand devices, I don't understand circuits, I only understand ones and zeros. All right, take this, give me your voltage mode logic circuit, put it into this black box, put it into your wire, which looks no different. Okay, and now the great advantage is because this is current mode, once and the voltage is not changing very much, once the current enters at one node, it can't get out. Where will it go from this wire? It can't boil off. Okay, so that current is sure to reach the other end as long as the voltage is not changing very much. It is not charging any capacitors. As a result, you don't need repeaters. Okay, so now that problem that I have reached a critical length of the wire and I look down saying, okay, give me some space, I need some real estate here for a buffer, and find that there is no real estate available. Either I elbow aside some existing circuit, relay out, etc., or go to a non-optimal wire length and put the buffer there. That problem is not there. Simply look, no buffers. Okay, so just honest to God, transmitter at one end, receiver at the other end, and a plain wire between the two. So we are back to good old days when connections were connections and did not demand this. So I think that's a very big plus point for this. However, one has to be realistic and there are a few disadvantages to this. So now stop celebrating. There are certain flies in this ointment. First, unlike most CMOS circuits, this solution takes static current. Okay, because the circuits are analog circuits and they draw power all the time. Therefore, this is not a very good solution if you don't want high speed. Okay, so we simply declare that we are the Mercedes. Okay, and you want a Maruti, go to Maruti. We sell you Mercedes. You want high speed, low power transmission of data, come to us. If you don't want, then what you should do is to have a buffer and send the data very, very fast and then turn off this thing so that you don't waste static power. But if you send data at low speeds, then we have a disadvantage because we always draw this much current and therefore we consume static power. Okay, so therefore we don't look so shiny when the data transmission is at low speed. Over long period we will consume huge amounts of power. Okay, so we need to turn these things off, and that is one big problem for this. It works only for this. The other thing is that there is actually one problem which we have still not solved, and that is what our next attempt